This is chapter 15, Weathering Slopes and Unstable Slopes. Our goals for this chapter include to introduce the processes and landscape features of weathering. We will also investigate the process of soil development and some general features of soils. We will also look at factors that control slope stability and the types of slope failures, and look at the impact of slope failures on society. All right, we'll start here in the northern coast or along the northern coast of Venezuela. It's a perspective from satellite data. We're looking at Caracas with respect to mountains and valleys. All right, so in this region we have scars left by landslides. We have an image of an urban area impacted by a landslide. Large erratic boulders from those pathways and some damage to a building. Some observations we can make is the cities are built on flat areas. The flat areas are at kind of the foot of some mountain valleys, and they're fan-shaped. And they're built here. Unfortunately, they're next to mountains and they can be impacted by landslides, but they're built here because the other areas are too steep to build on. So in this area, there was heavy rain in 1999. It caused massive landslides, debris flows that went down canyons. They carried those car-sized boulders into town, destroyed entire neighborhoods, and killed at least 19,000 people. Through the cleanup here, the USGS and Venezuelan geologists discovered houses built on older debris flows with huge boulders. So it makes sense why you live here, because the slopes are too steep to build on, but unfortunately there's been a history of landslides that are pretty devastating. Okay, let's talk about weathering and jointing of earth materials. So the diagram in the top left shows some pre-existing joints from perhaps burial, tectonics, or cooling of rock. And the size and spacing of joints, just some separation between materials. These are the joints. There isn't real lateral displacement. But the size and spacing of those joints varies from rock to rock and place to place. Now, expansion joints form as pressure decreases when rock is brought up from depth, and then unloading can cause thin slabs to peel from rock. We call that exfoliation. You have a reduction in pressure, so there's unloading. So in a landscape, we're looking at a certain amount of jointing. This is from Massachusetts, or a certain frequency. We look at the spacing of joints. There's a lot of room between these joints from South Dakota. And this is an example of exfoliation, where the top is sort of falling off the rest of the rock in Texas. And that brings us to physical weathering processes. So, simply put, physical weathering breaks rocks into smaller pieces. With heat and cooling, you can have daily and seasonal thermal expansion of earth materials, which imposes stresses on the boundaries between minerals and causes microfracturing, like very small fractures. You can also have frost wedging, and that's when water that's within a fracture or a joint freezes. It expands, say, 8% and exerts a strong outward directed force on the walls of the fracture. You can also have mineral wedging, where water and fractures might precipitate crystals of salt, calcite, or other minerals. And then as those grow, the crystals exert an outward force on the fracture. And you can also have root wedging. Plant roots can grow and extend into fractures and further open them. And burrowing animals can also, bring material to the surface and physically weather material. So how does fracturing affect weathering? This is, a cube. We're looking at the surface area. One side of the cube is 2 centimeters by 2 centimeters, so that's 4 centimeters squared. Okay, and if you had 6 sides, you'd have 4 centimeters squared times 6, and that would be 24 centimeters squared. And the truth is that fracturing increases the surface area. Okay, so we fracture the cube into pieces. Okay, in this case, you have one side. 1 centimeter by 1 centimeter is 1 centimeter squared. If you had 8 cubes, you get 1 centimeter squared times 6 sides times 8 cubes. That gives you 48 centimeters squared. So the rate at which that material will weather will go up with more fractures because we get more surface area exposed. Okay, we'll look at this block diagram and think about how changing the environment that a rock is in would promote further weathering. Okay, so say you have granite that was formed beneath the Earth's surface under some specific pressure and temperature conditions. But if it's uplifted, like in a mountain, it's now subjected to new temperature and pressure conditions. So it's also now at the surface where it can be physically broken. And rocks formed at high temperatures and pressures might not be stable on the Earth's surface as they interact with atmospheric oxygen or water, which can break down their mineral bonds over time. Okay, so how do Earth materials dissolve? Well, you can have little pits formed when parts of the minerals, go into solution. You can have existing fractures widen over time. You can have rounded edges and corners, right? So we see pitting in this photograph and then widening fractures or joints in the second one. And let's think about the mineral calcite. Okay, so calcite in the presence of carbonic acid can dissolve, and we will then yield the calcium ion and the bicarbonate ion in solution. And we then have this void space where it was once a solid calcite. Okay, so near the Earth's surface, let's talk about oxidation. So this reaction is pyroxene in the presence of oxygen, yielding hematite, which is an iron oxide, and silica in water. Okay. And what that will look like is something like this. Hematite is red in color. All right, so this is a boundary from the Jurassic sandstone near Las Vegas. It was a boundary between oxidizing and reducing fluids. All right, so oxidizing and reducing. Got it? And then here's an example of hydrolysis. Okay, so potassium feldspar plus water will then yield kaolinite, which is a clay mineral, and potassium in water and silica in water. And that can look something like this. And we see a lot of weathering due to hydrolysis in hot and humid climates like the state of Georgia, for instance, is known for its red dirt and kaolinite. So this rock is dissolved and parts of it are converted to red clay. Okay. Weathering can also increase the salinity of the oceans, shown here. So rock, sediment, and soil on and near the Earth's surface are exposed to water and to oxygen in the atmosphere. And then some water infiltrates into the subsurface where it may chemically react with the materials. And during weathering, hydrolysis reactions commonly produce clay minerals and they drive out positive ions. And then the dissolved cations, along with negative ions like chlorine, are carried by moving water, much of which will then find its way to the oceans. Modern oceans contain about 3.5% dissolved salt. And when seawater in the oceans evaporates, the dissolved salts remain in the seawater, which even more so increases salinity. Okay, so there are some controls or factors that control how different minerals weather, and that includes climate, the time exposed to weathering, the chemical composition of the minerals, and the atomic structure of the minerals. So calcite has pretty weak bonds and it readily dissolves in water in the presence of an acid, especially. Quartz has strong bonds. It's much less soluble. So it'll look like this. On the left, limestone is calcite, typically very soluble, and most sandstone is less soluble quartz. The point is that different minerals weather differently based on the strength of their bonds and the existing chemistry that they're subjected to as well. Okay, so when granite weathers, we have feldspar weathering by hydrolysis into clay minerals. Feldspar is the most abundant mineral in granite. Okay, and then clay minerals can accumulate in soil or be eroded and transported by water. The mafic minerals form clay minerals or they oxidize to hematite. So you'd see some red clay from that type of weathering. So the mafic minerals can include biotite or magnetite as well. Remember that quartz is very resistant to chemical and physical weathering. And the quartz grains erode from the granite and they just typically become quartz sand, which would then accumulate along rivers, dunes, beaches, things like that. Okay, so more factors here that can influence weathering. The composition, the type of minerals a rock contains influences how it weathers, as we spoke about. The variation in composition matters too, because some outcrops have different parts with large contrasts in susceptibility to weathering. And then the amount of surface area matters too. Rocks broken into smaller pieces have more surface area on which chemical weathering can act. And then discontinuities can assist with more rapid weathering in terms of fractures and breaks between beds. And we'll look at the role of climate in weathering here. So climate reflects temperature, precipitation, and seasonality, which would therefore influence weathering plants and soil. Okay, so what we see here, if you have, a lot of heat, a lot of precipitation, this is this is representing temperature and precipitation, you're going to have a greater depth of weathering. So tropical is where we see the most weathering of earth materials. Okay, subtropical, a lot less precipitation, but still a high temperature, kind of not a whole lot of weathering. Mid-latitudes, we have a moderate amount of both, so we have a moderate amount of weathering. And then polar regions, more precipitation, temperature is very low, so pretty low weathering rate compared to tropical areas. And then slope, now that influences weathering as well. It matters which way a slope faces. We call that the slope aspect. Sunny slopes have less soil, plants, and chemical weathering, and then shaded slopes have more soil and plants on them. Windward slopes receive more precipitation, call that the orographic effect, and then gentle slopes retain soil and moisture and accumulate material from higher slopes, falling down with gravity toward them. So, time influences weathering because biologic activity causes weathering. That's the life part, such as roots breaking apart rocks and plant-derived acids attacking materials in the soil. And then time is a crucial factor in weathering. If you have more time, you'll have more weathering. As seen with this, I believe, marble headstone. And I think that says 1882. So we've had time to weather this. So weathering will produce rounded features over time. First, many rocks will have sharp angular edges. Over time, the edges and corners begin to smooth until we have no sharp edges or angular features whatsoever. And then we can kind of see a weathering rind as an example of that developing over time, or spheroidal weathering as in the case of this. And how do caves form? So what we really have is a block of limestone. Most of them are found in limestone. Limestone's incredibly soluble because it's mostly calcite or similar carbonate minerals. Groundwater perhaps carries carbonic acid and readily dissolves the material, and they'll widen over time because dissolution widens those bedding planes and fractures until they become cavities in caves. Part of that cave above the water table might be mostly dry, but the cave below the water table will contain water that further dissolves the material and enlarges it over time. If you wonder about sinkholes, a sinkhole can develop over the collapsed part of the cave, say on the right side. A cave might not have any expression on the surface at all. Like, say over here, you don't know it's here at all, but there's a small opening. Okay. We'll think about more cave features. So, the roof collapse of a cave can form a sinkhole on the surface. So, if you built your house here, it could be bad, theoretically. Water dripping off of the roof of the cave evaporates as well, precipitating calcite and other minerals in the form of stalactites. Minerals build up cave formation from the roof, floor, and walls. Stalagmites are what's on the ground. So all of this put together is what we call a karst topography when we're looking at the surface of where caves are. That'll have sinkholes, perhaps limestone pillars, disappearing streams. If the cave is filled with water, it's less likely to collapse because the water is helping hold up the roof. And if it's filled up with water, typical cave formations aren't forming because there's no drips or evaporation. And this can change over time. Like, some caves may have been partially filled with water or were once dry, and then they've since been refilled when the water table rises again. And the point is that water in caves can flow or be stationary. Okay, so more on karst topography. That's produced by weathering and erosion of soluble rocks. You can have these sinkholes and pits formed by the collapse of caves. And then stream drainages that are captured by pits. We call those disappearing streams. You can also see things like pinnacles and dissolved rocks. Here's a spatial distribution of karst in the United States. I'm thinking, of course, about our region of Michigan. We have unexposed evaporite rocks. Some of them are exposed due to gypsum mining here. The tip of the thumb has evaporites. All right, and then karst around Alpena into the Upper Peninsula. You have exposed and unexposed. And for some reason, we've included volcanic rocks. Why not? All right. Here's a cut through a soil profile. This is from Montana. We call soil layers horizons, and we assign them different letters. Okay, so we have O as organic material at the top, then organic material and mineral grains, a leached zone leading into clay, iron oxides, and calcite in dry climates into the weathered bedrock and bedrock itself. Not all soil horizons are going to be present in every soil profile, of course. That depends on the climate and whether or not the top has eroded away over time. So thinking about the processes of soil formation, it really forms slowly over thousands of years. And it involves some of the same processes as weathering, including dissolution, oxidation, hydrolysis, and root wedging. Soil formation also involves the vertical transport of dissolved material up and down through the soil profile, and we kind of see that here. So weathering does weaken the underlying bedrock. Ions can be leached from the upper part here. You can have gas from roots interacting with the soil profile. Clay and fine particles can work downward. And you can also have an accumulation of calcite in dry climates, not in the presence of water. So here's some soils in tropical climates. We talked about those having the greatest rate of weathering due to high temperature and high amounts of precipitation. So abundant rainfall leads to intense chemical weathering and washing of material out of soil. From that, you get a lot of clays and leached materials. We can call that a laterite, an extremely leached soil. And in temperate conditions, that's cooler with less rainfall, we're going to see grasslands, forests, and farms. There's enough moisture to leach soluble material out of soil, right? And then in arid climates, those are dry, generally hot. You'll have less chemical weathering and material leached from the upper parts of the soil, accumulating further down. And then calcium carbonate, calcite, precipitates in the soil, building up over time and forming what we call a caliche over tens of thousands of years. Not being dissolved into solution because there's not a ton of water available. So what threatens soil? Overgrazing is one thing. Removing vegetation and clear cutting is another thing. Erosion. These are all sort of human-led activities that we're talking about because those are livestock in the top left. You can do terracing like this to prevent erosion, but soil contamination is another issue. For example, salt buildup and over-application of pesticides that threatens the integrity of the soil for supporting life. Okay, so some soil-specific problems that can be hazardous. Liquefaction is something that occurs in conjunction with an earthquake. So ground shaking can cause saturated sediment to lose grain-to-grain contact and then strength. And a building sitting over it could then just be sucked into the soil. Not good. So areas that are along water with saturated soils and ground shaking are subject to this risk. Swelling clays is another thing. Clay incorporates water between sheet structures and then swells when wet, and then it shrinks when dry. And that, among other things, is why a lot of our roads, say in the Saginaw Bay area, don't last too long, because we're sitting on clay. And we have a lot of freeze and thaw. We're swelling and then contracting and shrinking. So, yeah, something to think about. Soil compaction as well. Compaction of clays and other sediment can cause the ground to subside, perhaps unevenly, and then we could see this affecting a building. Perhaps this crack was caused by compaction. All right, so we'll move on to slope stability and start with the role of gravity in slope stability. Gravity acts vertically, so this block here is not going to move on a flat surface. The main force responsible for something sliding down a slope and mass wasting, we call it, is gravity. And the force of gravity acts everywhere within and on the surface of the earth, and it tends to pull everything toward the earth's center. Okay, so you have this block on a slope. The force of gravity is our normal component, but then there is a shear component to that block sliding down a slope. And the normal component pushes the block against the slope. The shear component pushes the block down the slope. So how steep can a slope be and still remain stable? So this is dry sand being poured into a little hill. What we have here is an angle of repose. And there's a critical angle to which sand can be piled up before that sand just collapses down slope. So here's a sand dune. We have an angle of repose for dry sand. A talus slope. Some parts of this slope were steeper than the angle of repose, so they continue to slide downward. And we see that as well with this scoria cone, where coarse material can have a steeper angle of repose before the slope fails. Okay, so some factors that control slope stability. One would be the angle of repose for the material. How steep can this thing get before more material moves down slope? The amount of water acting on the area, and then discontinuities such as fractures, cleavage, and bedding. Loose materials like soil might have a typical angle of repose, but solid rock can hold steeper slopes. And then adding too much water to loose materials can weaken them. Rock is weaker as well if discontinuities are oriented so the rocks can slide downhill. And then we'll look at some events that could trigger slope failure in this landscape. All right, so we have precipitation here. If there's a change in land use, such as overgrazing, deforestation, weakening soil, or building towns on top of soil, we could have this area impacted and perhaps less stable slopes. Like if you overload material here, that could change and overload the slope. Let's see. The slope can also be undercut by rivers, waves, or highways. which could cause it to fail. And then sudden shock, like from an earthquake, could result in slope failure as well. And certainly volcanic eruptions could play a big part in slope stability. And you can see that has a nice little landslide here. I'd say this is partially due to the presence of precipitation water assisting the landslide there. All right. So we'll look at some ways that slopes can fail. This is an undercut cliff. There's water at the base, and we see slope failure in Utah. Earthquake activity triggered this slope failure. The slope is just simply too steep, so it failed. A landslide. This could have been triggered by precipitation. Not sure. And then undercut slope. We have a road built through here and a failure right over the road. Might have happened without the road, but still. Okay, so geologists can classify slope failures, or engineers, by a few different things. One would be the mechanism of movement, whether it was just a simple fall of rock blocks or flow of materials like here. The type of material, was this solid rock or was it unconsolidated? And then the rate of movement of material down that slope. Was it fast and devastating like this, or was it a slow creep as in this landscape? So what happens when rock or debris falls? We're showing you kind of an example of a block diagram of that versus a real example in Canyon Lake, Arizona. The fall must be associated with a cliff. Large blocks below the cliff may indicate the potential for fall. So if you see blocks at the base of a cliff, you know it's probably likely to happen again. All right. Then sliding, by contrast, that's where you have a somewhat intact block at the start of the movement that typically detaches along a bedding plane or a fault or some other kind of discontinuity. You can also have a rotational slide. That's where curved surfaces in either rock or loose materials develop. Those are also called slumps. And then rotation tilts layers if they are present. Here's the basic geometry of a rock slide. And rock slides require sufficiently steep slopes along with bedding planes, fractures, or other flaws that are inclined to downslope. We see that motion down this way with detachment and then a place to slide. You gotta be able to move somewhere. Nothing's holding it up. So then that leading edge overruns the land surface and leaves behind a scar or a scarp, we can call it. All right. So this is a disaster that happened in Italy with a dam built in 1960. We're showing just a block diagram of it. A landslide, which was actually a rock slide, occurred after heavy rain in 1963. And from that displacement, there were waves that killed 1,000 people around the reservoir. The dam was not destroyed, but it was overtopped by a wave. And then, unfortunately, 2,000 people were killed downstream from that dam. So that huge block, it detached along the beds. It slid into the reservoir. It flooded nearby towns and then continued to flood downstream towns with overtopping of the dam. All right. So here are some slope failures that involve flow or weak materials. Things are constantly creeping, like hills are creeping right now as we speak, downward due to gravity. That's a slow, continuous movement in weak materials. Like I said, it occurs on most slopes, but at different rates. A debris slide that's unconsolidated, but it detaches along some interface. And then an earth flow. That's a weak flow with a matrix of fine-grained materials. It moves like wet concrete. It's also called a mud flow, more commonly known as that. Okay, so a debris flow again. That's where you have loose slurries with various sizes of clasts that can move rapidly. A rock debris avalanche, that's a collapse of a steep slope, followed by a high velocity flow and shattered pieces of rock. So slope failures in the United States. We had a debris avalanche in Alaska following a 7.9 magnitude earthquake in 2002. Those came down as a result of the seismic activity. In Tully Valley, New York, we had an earth flow or a mud flow, also known as a landslide, in 1993, which mobilized clay deposited in a glacial lake. Quite muddy. And then in Washington, we actually had the deadliest landslide in U.S. history in 2014. And in Utah, we had the Thistle landslide. That was the costliest landslide in U.S. history. It buried a railroad, 2 highways, and a town in 1983. All right, so landslides in La Conchita. This is a coastal California town hit by landslides in 1995 and 2005, and then one earlier in the 1980s. So the same area or adjacent area was hit each time. The adjacent area was kind of an identical setting. The geologist's recommendation is just to abandon this town and not live there anymore because the risk is so great. And thinking about risk across the lower 48, we're seeing red as high potential for landslides, yellow and green as intermediate, unshaded as low or unknown. So I want to highlight some things if I could. I'm going to open this in Google Earth because I think this should be highlighted. Many people wouldn't think of, say, the Saginaw Bay is at risk for landslides, but in fact, we have intermediate risk here. Here we go. All right, so lower than some parts of the lower peninsula, but the reason for this is just a huge drainage basin with multiple rivers feeding into the Saginaw Bay that can carry town and have an we're still going down in elevation quite a bit. This whole area was formed through drainage, and we're still draining. And then I'll also point out that these yellow parts along the coast, intermediate risk for debris flow, they actually, they're impacted by Lake Michigan. Some of them are tall sand dunes, constantly being reformed through natural processes. And we see that. I would mark more areas, but I'm not sure how this was originally developed, just from what I've seen working for the state of Michigan. But that's another intermediate area for risk. Around Lexington as well, it's quite a steep slope into the lake there. So, yeah, in the UP, the Keweenaw, this is more mountainous. So we have and intermediate to high potential for landslides. And just ignore this. This is from the plate tectonics exercise. All right. So that's what we're looking at locally, but obviously mountainous regions with great contrast and elevation are going to be our highest potential for landslides, but anywhere you have a drainage system, you got to think about that as well. We can recognize past or prehistoric slope failures through, say, hummocky topography. We call these hummocks. This is in British Columbia, Canada. Prehistoric landslide deposits, like in Venezuela. Broken angular rocks that you can see right in front of you. You know this has slid down in the past and it continues to do so. Or a scarp where material fell down and left this vegetation-free scarp as well. So to assess the potential for slope failure, we can look at past failures, known problems that we can see right in front of us, steep slopes, changes in slope, conditions of the material, and potential triggers. I would also add presence of water and drainage basins to that as well. And with that, we will stop here for today.